Now we'll go to our second part of the video. Here we will design transverse reinforcement for a RCC column using our calculation sheet. Here you can see that I have mentioned the colors of the fields in this calculation sheet. The white colored fields indicate the input fields, and if the design results are satisfactory or adequate, that field will be colored as green, and if any of the design result is inadequate, that field will be colored as red. So here you will see that I have provided two options for the member type design. One option is column and another option is boundary element of walls. Also for code, I have included two options. One is ACI 31819 and the other is BNBC 2020. Here I have created a simple model just to show you the design steps or the process to design the transverse reinforcement of RCC column. This is a 6-storied RCC building and the framing system is special moment resisting frame. At first we will design the transverse reinforcement for the Y direction. Here this is the cross section of our column. The column size is 24 inch by 36 inch. Here we will call this face C1 and the other face C2. In the C1 face I have provided 9 number 8 bars, which is actually 25 millimeter bars, and in the C2 face I have provided 6 number 8 bars. Now at first we will determine the transverse reinforcement requirement perpendicular to this dimension C1. That means the transverse reinforcement will be placed in this direction. So in our calculation sheet we'll select the member type as column and the design code ACI 31819, and we will input the compressive strength of concrete 4 KSI and yield strength of reinforcement as 60 KSI, and the value of C1 will be 36 inches and the value of C2 will be 24 inches. The clear cover value is 1.5 inch and the height, which is actually the clear height of the column, will be 11 feet. And the smallest longitudinal bar diameter is 25 millimeter, which is number 8, and the value for phi as per the code is 0.75. Total number of bars which are provided in the column is, here you can see that the total number of bar is 26. So we will input that in here, and for the number of bars along C1 we have provided total 9 rebars in that face, and in the C2 face we have provided 6 bars. Here you know that the first step of our calculation is to determine the value of L0. In here it is already determined, which is 36 inches, and the value of maximum allowable spacing, which is the maximum allowable vertical spacing of transverse rebar in the non-critical region. That means we know that the spacing of transverse rebar in the region of L0 is termed as S0, and the spacing of transverse rebar other than that critical region is termed as S. There are some parameters for this spacing value which we have to determine also. Here the value is already determined considering these three parameters, which is 6 inches. Now let's go to the second step to determine the spacing of the transverse reinforcement in the critical region. In here we have to input the provided tie bar details. At the initial process we will just input some initial values and check whether these values are adequate to fulfill the requirement of the code provisions. Let's say that we will provide the diameter of the tie bar as 12 millimeter or number 4, and the spacing of the vertical spacing of the tie bar, which is S0, let's say we'll consider 4 inches, and the total number of tie bars along that direction, which is perpendicular to C1, we will provide total 4 numbers. Here you can see that along the perpendicular of the dimension C1 there are actually 1, 2, 3 and 4 numbers of tie bars. Let's see that if this provided tie bar detailing is adequate or not. In here the first criteria we will check about the required shear strength. To do that we have to include the maximum axial force. So let's go to our analysis model and determine that axial force. So at first let me show you in what combinations we'll consider to determine the value of maximum axial force PU. Here this is the load combinations mentioned in the BNBC 2020. Among these combinations the earthquake load is included in number 5 and number 7. So for the value of maximum axial force PU we will consider only these two combinations. Similarly in the ACI code you can see that these are the design load combinations. Among these combinations in E and G the earthquake load is included. So for the axial force PU we will only consider these two combinations. Now let's go to our analysis model to determine the axial force PU. Here you can see that I have included all the design combinations which are mentioned in the code. Among these combinations, as we have to only consider the series 5 and series 7, I have prepared the envelope including these combinations only. You can see in here that for the earthquake in X direction I have created an envelope for the series 5 load combinations and created another envelope for the series 5 load combinations in the earthquake in Y direction, and similarly for series 7 also I have created the envelopes. From these envelopes we will determine the maximum axial force. So let's analyze our model and get the value. So our analysis is done. So for the design, let's consider this column of the first floor in here. Here you can see that the entire elevation of grid B is shown in here. Let's get the maximum axial force for the earthquake in Y direction for the series 5. Here you can see the value is 997 kips, and for the series 7 the value is 395 kips. Let's write down these values for our calculation. Now here we have found that the maximum axial force is 997 kips. Let's put that value in our calculation sheet, and the minimum axial force we get 395 kips. Let's input that in here. Now in here we have to determine the corresponding probable moment regarding this value. To do that, we have to generate the interaction diagram. If you click on here, you will get the link to generate the interaction diagram. So we will use this calculation sheet to design and generate the interaction diagram. To do that, we have to provide the dimension details and reinforcement details of our RCC column. So in here, as we are designing the transverse reinforcement for the columns in y direction, this face will be termed as C1 and this face will be termed as C2. So therefore the C1 value will be 24 inches and C2 will be 36 inches, and the compressive strength of concrete will be 4 KSI. And here this is the tensile stress actually, which we have mentioned earlier, that this has to be the 1.5 times more than the yield strength of reinforcement. As the yield strength of our reinforcement is 60 KSI, if we multiply it with 1.25, the value will be 75 KSI. Therefore the tensile stress for the interaction diagram will be 75 KSI. Now you can see that the total number of rebar layers is 9 here. So we will input the number of rebar layers as 9, and you can see that the layers as per the input value is generated. Also the distance of the layers from the column face is also generated. Now we have to just input the area of the reinforcement in the each layer. As you can see that in the first layer there are actually 6 number 8 rebars. So the area of one number 8 rebar is 0.76 square inches and total rebar area will be 4.56 square inches. So let's put that here, and for the last layer the value will be same, which is also 4.56 square inch. Let's put that down here, and you can see that in the middle layers there are 2 rebars in each layer. Therefore the total area of those rebars is 1.52 square inches. Let's put that in the middle layers. Now the total rebar will be calculated as per the provided rebars in here. Here, as per these design parameters and reinforcement details, our interaction diagram will be generated automatically. So I want to mention here one issue, that as this is generated using JavaScript, so when you enter this first page, you should reload this for the first time to get the proper JavaScript effect. Now you can see that the values are generated in here, and you can see that the balanced point is generated, and the maximum probable moment is found in that point, which is 2187 cube feet, which is also highlighted in here. Now let's get our corresponding probable moment for our maximum axial force. Our maximum axial force was 997 kips, and the corresponding probable moment for that axial force is 2121. You can see that this value is also mentioned in here. Now let's put this value in our transverse reinforcement calculation sheet. Here we have to input another value from our analysis, which is the shear force determined using the load combinations. So the shear force in here is the shear force generated from the probable moment ampere, and this value of shear force is generated from the actual load combinations from the analysis. So let's get that value from the ETABS model. So to get the design shear force from the load combinations, we have to design the concrete members. So let's start concrete frame design. After the concrete design is finished, right click on the particular column and go to the details, and in here let's go to envelope. Here for shear force in direction VU2, the maximum shear force is 56 kips. So let's put that value in our calculation sheet, which is 56 kips in here. Now here, as the shear force generated from the probable moment is larger than the analysis model, we have to consider this value for the design of the transverse reinforcement. In here, for this shear force, our required maximum allowable spacing is found 4.1 inches. You can see that we have provided 4 inches spacing. That means our provided spacing is less than the maximum allowable spacing. So our provided spacing is okay regarding this requirement. Now let's go to the second criteria, which is the minimum transverse rebar requirement. Here it is a check if the axial force is larger than 0.3 FPM/CAG or compressive strength of concrete is greater than 10,000 psi. You can see that none of this criteria is triggered in here. So that means, which we have discussed in earlier, we do not have to consider the equation C. Now let's check the other provisions. As per the code requirement, the maximum allowable spacing is found in here 6 inches, and which is also adequate because our provided spacing is 4 inches. And there is also a minimum value requirement for the feasibility of construction, and which is 4 inches, and our value is also satisfied regarding this requirement. Now here is another check, which is the value of HX. As this criteria is not triggered, the maximum allowed HX value is 14 inches, and you can see our HX value is 3.9 inches in here, which is also fine. Now as this case is not triggered, for the requirement of ASH, we have to consider only equation A and B. We do not have to consider equation C. If this case is triggered, you will see that there is another field which will show you the result for the ASH requirement using the equation C. For example, let's increase the axial force value, let's say 1500 kips, and you can see that another field for the ASH requirement is generated in here using the equation C. Let's go back to our initial value, which was 997 kips. In between these two equations, the value of 0.8 square inch is governed in here. Now, as per our provided detailing, the provided area of transverse reinforcement is calculated in here, which is 0.7 square inches. You can see that this value is less than the required ASH. Therefore, the demand capacity ratio is more than 1. So we have to reduce it. Now let's increase the number of tie bars. Let's provide 5 numbers of tie bars. As you can see that the demand capacity ratio is now less than 1. So our provided transverse reinforcement is sufficient for all the requirements and code provisions. So therefore, the final rebar details will be number 4 bar, and spacing will be 4 inches for the L0 region, and the total number of tie bars will be 5 numbers. Here you can see that in this cross section there are 4 number of tie bars, but for our column in the perpendicular to the dimension C1 we have to provide 5 numbers of tie bars. And the spacing after the region of L0, the spacing of the S will be 6 inches, which is generated in here. So this was the design of the tie bar for the perpendicular to dimension C1. Now let's design the tie bar for the perpendicular to dimension C2. Now to design the tie bar in the perpendicular to the dimension C2, we have to input some design parameters similar to the C1. Here you can see for the tie bars which are perpendicular to the dimension C2 is in here in this direction. There is actually in this cross section detail there are 3 numbers of tie bars. Now let's provide some initial tie bar details for the C2 dimension and check that whether it is adequate for the requirements. Similar to the C1, we will provide the number 4 bars, and the spacing we will also provide 4 inches center to center. And let's put the number of tie bars, 4 numbers. So in here we also have to input the maximum axial force. Now in here, as we are designing the transverse reinforcement for the x direction perpendicular, and that means the tie bars will be provided like this. As we are designing the transverse reinforcement for perpendicular to this dimension C2, we have to consider the maximum axial force including the earthquake effects for the x direction, and I have checked that the maximum forces for that direction is similar to the y direction which we have written earlier. So that means for the series 5 the axial force is 997 kips, and for series 7 the axial force is 395 kips. So let's put these values for our dimension C2 also. Now to determine the corresponding probable moment ampere, we have to input the rebar details regarding this direction. Actually, that means the direction which we have considered earlier for C1, that direction will be rotated in here to determine the interaction diagram for actually the minor axis. So our C1 value now will be 36 inches and C2 value will be 24 inches, and here the Fy will be 75 as well, and the number of rebar layers will be here for this direction, the number of rebar layers is 1, 2, 3, 4, 5, and 6. Let's put it down here, and let's input the total area of rebar in each layers. In the first layer, there are 9 number 8 bars. So total area of rebar will be 0.76 into 9, which is 6.84 square inches, and end of the layer there will be also 6.84 square inch rebar, and in the middle layers there are 2 number 8 rebars, and the total area will be 1.52 for each layer. And the interaction diagram will be updated as per the reinforcement details. Here you can see that for the axial force, corresponding probable moment was earlier, and the value was 2121 kip feet, but now for the minor direction the value is now 1488. You can see also in here for the corresponding 997 kips, the corresponding probable moment is 1488 kip feet. So let's put that value in our calculation sheet. Also earlier we saw that for the shear design force for the view 3 direction was actually 58 kips, and similar to the dimension C1, for the dimension C2 the design shear force from the probable moment is governed. In here, to resist that shear force, as per the tie bar diameter, the required spacing of S0 is determined in here, which is 5.7 inches. This is the maximum allowable spacing, as we have provided 4 inches, so this value is adequate. In the next step, we have to determine the minimum transverse rebar requirement. Here you can see that this criteria is not governed in here, and the maximum allowable spacing requirement is 6 inches, which is also fine regarding our provided spacing, and the minimum spacing for constructibility is 4 inches. You can see that our value is equal to that value, which is also fine, and the value of hx is also in the allowable limit. So the governed ACH requirement is 0.5 square inch, and our provided transverse rebar is 0.7 square inch. So the demand capacity ratio is below 1. As this value is less than 1, we can say that the provided transverse reinforcement is adequate. Now our calculation process is finished in here. As you can see that the design fields all are green, that means all the provisions are satisfactory as per the provided tie bar. So the design of transverse reinforcement is completed in here. Now here you will find another option for the boundary element of wall. If you have to design the transverse reinforcement for the boundary element of special structural walls, you can select this option. You will have to input the design parameters in here. Here the LB is the length of the boundary element, and B is the width of the boundary element, and you shall input those values in here. And similar to the column, you will have to provide the initial design tie bar details to check the adequacy of the provided transverse reinforcement. Here also the value of S0 and the minimum spacing will also be checked in here, and the value of hx will also be checked, and the demand capacity ratio regarding the equations of governed equations of equation A and B will be also checked in here. Same as like that the column, you can design the boundary element of the transverse reinforcement. So the second part of our video, where we have designed the transverse reinforcement for RCC column, is finished in here. I have written this article and the calculation sheet so that the design professionals and the students can learn and use this article and the calculation sheet for their requirement. So here you can see that I have included a comment section right below the calculation sheet. My request will be to you that please provide some feedback after using this calculation sheet. Also, if you face any problem or if you found any mistake in the article or in the calculation sheet, please mention in the comment section. I will try to update the article or the calculation sheet as per the correction. Also, if you have any queries regarding this article or the calculation sheet, you can also comment in the comment section of this YouTube video. Also, please hit the thumbs up button if you like this video. Also, please subscribe to the channel for the future tutorials. Thank you. Allah Hafiz.